Hello, my name is Wade. I recently developed an Excel spreadsheet that allows the user to model what a 100% renewable energy supply would look like on grids such as the USA or Germany. Now, this presentation is going to be in a few different parts, so there's going to be parts 2 and maybe part 3 following this first video. In this first video, I'm just going to do an overview of the model, a brief explanation of how it can be used to model putting different amounts of renewable energy into the grid and the results you'll get as you make those changes. Now, the point of the model is that it is interactive. You are able to make changes to it. So what you will need to do is, if you want to use it, you'll have to download it from my Google Drive account. You can do that by going to the links in the description of this video. The first link will be to the copy, will allow you to download the model from my Google Drive account. Now, what I'm showing you here isn't the current model. This is an old one that I did for the Australian grid, but I'll use it to demonstrate how to download this spreadsheet. So all you need to do is go to the description section below the video. There'll be a description here saying something like Google Drive link for the 100% renewable energy model for the USA or the 100% renewable model for Germany. There'll be two different ones. All you have to do is left click on the link. That will open the spreadsheet in Google Sheets. Now, you should not try to use it in Google Sheets. There's more than 100,000 calculations every time you make a change to the spreadsheet, so it takes a very long time to run if you try to use it in Google Sheets. It is better to download it. So go to File, left click on File, and then download Microsoft Excel as a Microsoft Excel document, and that'll send a copy to your computer. Once there, you can make a backup copy in case you accidentally make any changes that cause the model to stop working. Okay, so now a brief description of how it can be used and its basic operation. So the model works by taking real data for the American spreadsheet. It takes data from the US Energy Information Administration, the hourly electric grid monitor page. If you scroll down to the fourth graph here, you can use settings to select the time when you want the data from, and then download it as a CSV for Excel. You can download it up to a month at a time, so I downloaded the data for 3 years from the beginning of 2021 through to the end of 2023. So I have 3 years of data. I'll add to it in future, but you can download your own data for previous years if you want to. Okay, for the German data, I obtained that from the Fraunhofer Institute website, the Energy Charts web page. You go to this web page, it shows grid data for the electricity grid. You can choose a longer time period up to a year. And again, I downloaded the data from 2021 through to 2023. And then you can go down to the bottom of the page to export, and you can export it as an Excel file. So that's where I obtained most of the data from for the electricity grid. I'll get to the other data later. So I use this data to gain information about the grid. For the US, information about onshore wind production, PV production in real time. It's hour by hour data. So starting at midnight on the 1st of the 1st, 2021, then hour by hour throughout the entire year for 2021, and then the same for 2022 and 2023. There's 365 days times 24. I think that's 8,760 lines of calculations. Of course, it's every hour for the year. For the US, it has the nuclear output at that time, 95 gigawatts. We can see back here, I've got what the data looks like. So this is from the US Energy Information Administration website. What the data looks like. They have wind, solar, hydro, other. So this is the fossil fuel generation, nuclear generation. I use this data to calculate capacity factors for wind and solar. You'll have to look, if you're unsure what capacity factor means, it just means the percentage of the maximum's installations of wind or solar on the grid at the time. So in first half of 2021, there was approximately 123 gigawatts or 123,000 megawatts of wind capacity. And at midnight on the 1st of the 1st, it was producing 49,120 gigawatts, all the wind generators across the US. So that's 39.9% of their maximum capacity. Similar for solar. Nuclear, I took the actual amount, 95,251 megawatts or 95.251 gigawatts, and I just used it directly. We got demand by the sum of these generations, all these generations, so 418 gigawatts. I've converted all these to gigawatts because I work in gigawatts on my spreadsheet. For Germany, it looks much the same. It's every 15 minutes, but I only took every hour because I didn't want 4 times as many calculations because it takes a long time for the spreadsheet to process that. So again, they just have the power being produced at those time intervals for each of the types of generators. From them I can calculate capacity factors for the wind and solar and whatever else I might need. Okay, so back to the spreadsheet. So I get those wind and PV capacity factors, the total amount of nuclear. I use them to calculate the total amount of power that could be generated by different capacities of wind and solar and nuclear in the case of the US model. For the German model, since they've closed down their nuclear, I have offshore wind, onshore wind, PV, and run-of-the-river hydro as the main power sources, the main generators, mostly the offshore and onshore wind and the solar. Let's go back to the American model. Okay, so once I've calculated the total power coming from each of those sources, and I'll explain why I'd have to calculate and why I can't use the actual values from the data from those organizations. I compare it to demand. I calculate whether there's a surplus of supply or a deficit of supply, so supply minus demand. If there's a surplus of supply, as we can see here, that surplus can be used to charge storage types such as pumped hydro, batteries, whatever else, electric vehicle, batteries in electric vehicles, so three different types of storage, pumped hydro, batteries and EVs. So that's the next section of the spreadsheet. If there is a deficit in supply, if demand outstrips supply, then some power can be drawn from the storage types to help supply meet demand. So the next section of the spreadsheet calculates the amount of power that could be discharged from storage into the grid. The spreadsheet has been designed so that you'll never both charge and discharge at the same time. That is impossible, and it isn't going to. Well, it's not actually impossible on the grid because they have a lot of different individual batteries or pumped hydro dams or whatever. So some could be discharging while the others are charging, but I'm looking at the net amounts. So in net, you're not going to have equal amounts of charging and discharging. Okay, if after discharging from battery there's still a deficit in supply, so demand still outstrips supply, it calculates auxiliary supply. Now auxiliary is made up of 2 sources. It can be existing hydro capacity, so they have about 80 gigawatts of dams on the US grid, or hydro capacity on the US grid, much less on the German grid, only a tiny amount. And if after the hydro there's still a deficit in supply, then we have other generation. Now other generation in this column AM are sources other than wind, solar and nuclear and hydro. So for a 100% renewable grid, this would have to be renewable sources which are readily dispatchable. So it could be biogas generators, basically what the open cycle gas turbines do currently. So peaker plants, maybe biomass, because often the other generation will be needed for extended periods throughout the night when there's low wind supply and the sun obviously isn't shining throughout the night. So demand might outstrip supply. So biomass could run through the night, or as I said, biogas from the methane generated from sewage works and rubbish tips. And it could be gas turbines run from hydrogen, green hydrogen that's been synthesized using renewable power. Any sort of readily dispatchable source. You could even use, if you have a tiny amount of other generation, which this spreadsheet is designed to supply, then you could even use fossil fuel gases, because it would be such a tiny amount that could be offset. Okay, so after the other generation, supply will meet demand on the electricity grid. There are some other calculations which I'll get to later. The flexible demand, which I'll explain later. And then the rest of these columns are simply results, calculations, sums of results, etc., which are used in the results table, which is over on this right hand side of the spreadsheet. So that's the results table that I have here in this other window. Okay, so that's basically how the spreadsheet works. I'll go through detailed calculations, the details of how the calculations operate in a future video. Here I'm just going to explain how you can use the video to model different amounts of renewable energy supply and what it would look like for the grid. Now the outputs are in this table here, as I explained. So outputs are all these sections below here. It has, first of all, costs, which are just estimates. I'll explain more of that in a future video. It has demand, total demand. So currently total demand in 2021 was about 3.96 million gigawatt hours of electricity. Flexible demand at this point is just the power the energy used to recharge the storage types. Peak power during the year was 741 gigawatts. Percent of demand, so this is the percent of demand made by each source. So on the current grid, there's about 150 gigawatts of wind supply and about 90 gigawatts of solar supply. And this is the point of the spreadsheet, is that you can change the inputs to model different amounts of supply from different sources. So I'll get to that more in a moment, because that's the main point of this video. But the results show, as you make these changes, the results will change. So on the current grid, 56% of the supply is coming from sources other than wind, solar, hydro and nuclear. So that's basically the fossil fuel, the coal and gas-fired power stations. We're currently producing about 56.5% of the electricity supply. Wind about 11.5%, solar about 4%. These are the solar farms, the commercial solar farms, the utility scale ones run by large companies. There is also rooftop solar. I have not modeled rooftop solar in this spreadsheet. Instead, the rooftop solar, the production from rooftop solar is behind the meter, so it appears as a reduction in the amount of demand. Rooftop solar basically has the same production patterns. It produces a lot of electricity on the same day that the utility scale solar produces. Utility scale solar produces a lot of electricity in the same locales. So you can basically combine the two of them together. It doesn't make a lot of difference to how the spreadsheet works. Hydro produced about 8% and nuclear about 20% in 2021. Okay, then the actual absolute amounts in gigawatt hours. So for wind, it would have been 453,000 gigawatt hours that year. For solar, and so on. Curtailment is when there's more wind supply than is being used, and some of it has to be switched off. They close down some of the turbines. And on this version, there's currently zero curtailment. We'll see more of that later on. Capacity factors is the average amount, or the average percentage of maximum capacity that the wind and solar were generating at during the year. So over the entire year, wind was generating at 34.5% of its maximum capacity. That's a good value. Of course, it is very windy in the central third of the US. where they have most of the wind turbines. PV, average capacity factor, 20.25% for the year. That's a pretty good value for solar farms. Rooftop solar would normally be a bit lower, maybe around 12%, 12 to 15% on average across the whole of the US. Depends on where they are, whether they're in sunnier, drier states or in wetter, less sunny states, cloudier states. And then the last three tables are about the three different forms of storage capacity. The pumped hydro is the slow charging storage, the stationary battery storage, the fast charging storage, and the vehicle to grid, which is the EVs. Okay, other outputs are in graphs. So I have graphs over here on the right side. There's also a few on the left side, but these are the main ones. Just going to be looking at this bottom graph at the moment. So it's showing generation on the grid. The dark greenish greyish colour at the bottom is nuclear. The pale green above it is wind generated power. The yellow is the solar. The blue is the hydro, and the purple is the other generation. So in this case, in 2021, that would have been the fossil fuel output. Again, these are the hourly values, so each of these little grids is 1 day or 24 hours. We can see the dates up on the grid above here. So it's the 1st of the 1st at midnight. The next line would be midnight between the 1st and the 2nd, etc. Then the beginning of day 3rd of the 1st, and so on. So each of these little grids is 24 hours, so it shows how supply changed over the 24-hour period to match demand. Of course, an electricity grid supply always has to meet demand, otherwise you get blackouts. So supply is following demand here, meeting demand, but we can see that a lot of that supply is from fossil fuels, and that is the supply that we need to replace with renewables in order to reduce the air pollution, reduce the carbon dioxide and other particulate pollutants going into the air and eventually into the water. Okay, so we want to replace all of that purple, all the fossil fuel production, with the pale green, the wind, and the yellow solar. We do that simply by changing the input values for wind and solar. And I've already done that once. So these are up here. These are the inputs in the orange cells. These are the values that you will change to run different scenarios, or which I call builds. So different builds of the model. Now, what happens if we say instead of the current values of about 150 gigawatts of wind and 90 gigawatts of solar, we need to replace a huge amount of fossil fuels. So I'm going to go up to 1,000 gigawatts of wind, so increasing the current wind generation by a factor of almost 7, and 650 gigawatts of solar. Okay, so now we can see the graphs have changed. We can see that the outputs down here have changed. Previously it was 56% from other sources, now it's down to 2.6%. The wind was 11.5%, now it's up to 54.5%. The solar was 4%, now it's up to 20%. Nuclear has remained the same because they haven't changed the amount of nuclear generation on the grid. We can also see there's now some power, small amounts of power coming from the storages. I have the storage amounts up here, I'll discuss them more in a moment. So we can see from the graph here that there is now a lot less other generation and a lot more wind power, power coming from wind and power coming from solar. Those parts of the graphs are much larger. While the purple, representing the other generation, has decreased. There's still patches of other generation, and this is the main thing you are looking at when you're testing the grid. How does it look overall? Are there long patches where other generation requires a lot of energy? Because those are the toughest times for the grid. Those will be the toughest times. You can always reduce them further by increasing the amount of wind and solar, but that might become prohibitively expensive. It might be cheaper to have those small amounts of other generation being supplied by the biogas and biomass and by hydrogen powered generators than it would be to have more wind and solar, which might just be largely wasted apart from those few times of the year when they're struggling to meet demand. So the spreadsheet allows you to optimize the grid by looking at these things. So it's saying now we have the curtailed wind energy, 831,000 gigawatt hours, which is 27.5% of the total wind supply. We have curtailed solar energy, 29.8%. So of the total supply, the total solar supply, I mean. So I think that's a lot. Maybe there'd be a more cost-effective way to power the grid. So I have a cost estimate here. I'll explain in a later video how I calculate the cost of the wind and solar and the storage. But the other generations, basically, I look at the peak other generation, say 266 gigawatts, and I'm saying each gigawatt of that costs $1 billion to build a power station for. Most of these power stations might already exist. They could probably adapt many of the current open cycle and maybe the closed cycle gas turbines for using hydrogen, for instance. But just for the sake of the spreadsheet, I'm saying that we're building it all from scratch. So it costs $266 billion to build, and eventually you get a total cost down here, $1.378 trillion, or 1,378 billion US dollars. So the idea is to minimize this number. The other generation becomes increasingly expensive once it gets above 5% of total demand. So here it's at 2.63% of total demand. So it's more or less just $1 billion per gigawatt of generation capacity. If I had, say, a lot less wind and solar, so that the other generation was much larger, now it's 36% of total demand, we can see the costs going out of control. It just increased massively by a factor of 10. That's because the other generation is now supplying more than 5% of total demand. So I'm saying that once you get above 5%, it starts becoming increasingly expensive very quickly. That wouldn't be really true in reality, but I'm just doing that to emphasize the fact that we want to reduce the other generation as much as possible by having it look really expensive on the grid. Okay, so I'll go back to 1,000 gigawatts of wind. Okay, so now we're getting surpluses. We saw down here there was a lot of curtailment because there's surplus wind and solar at times. We can see the surplus on this graph up here, the top graph. The surplus are these light blue lines above the dark blue. The dark blue is the storage capacity, so the pumped hydro and the stationary battery storage. It doesn't include the EV at this point. So when the storages are at 100% of their capacity, they're fully charged, supply is meeting demand, and there's still excess wind and solar supply. So the pale blue line, we see there's a lot of it. So as I said, that surplus power can be used for charging batteries. So I'll look at the batteries here. We might think maybe we need more battery. We could use more battery supply on the grid. So you can change the amount of storage. So the pumped hydro, you can increase or decrease by changing the value in cell CV5. For the fast charging storage, the stationary batteries, you can change their value just in here. So any of the orange cells are input cells. They are cells that you can change to model different builds. I'm going to set them back to 300. The US grid probably won't need a lot of storage, relatively speaking. These are relatively small amounts, 300 gigawatt hours for each of the two. Basically because the wind supply is very good in the US. I'll just have a quick look at it. The wind turbines in the US currently are in these green areas. If you go to this website, you can scroll in to see exactly where the wind turbines are. You can zoom in. But basically there is a lot of wind capacity, a lot of wind coming through this central third of the US consistently. So east of the Rockies and west of the Great Lakes, or from the west and south of the Great Lakes, basically where all these wind turbines are built, there is a huge amount of wind blowing through the US, and it tends to blow both day and night, which is important, which makes it useful for meeting demand when the sun is not shining, so there's no solar power. These other places, there's also capacity for installing wind turbines here. Anywhere where there's a ridge line, there tends to be good wind generation capacity. We can see a small amount near Knoxville there. So anywhere where there are ridge lines. There are other maps you can find on the internet. I don't have them up here, that show where there are good places to put wind turbines. So a lot more wind turbines could be added in these places, and offshore wind could also be added. There's plenty of offshore wind capacity along the northeast, and I think along the west coast as well to some extent. Not so much down in the south in the Gulf of Mexico. Not a lot of offshore wind capacity there. Solar farms in the US, I may as well show this while I'm here, this is where the solar farms are, basically where the wind farms aren't. So a lot in California and along the east coast. And of course the wind farms are mostly in the centre. But again, you could put solar farms in the centre as well. They just wouldn't be as cost effective. They wouldn't work as cost effectively as the ones in these places because they get less sunlight than the ones, say, in Southern California, where it's sunny much of the time. But solar is very cheap, relatively speaking. So it wouldn't be as cost effective, but it would still be suitable for use. Okay, so you can change, as I pointed out, you can change the amounts of storage here. Now, there are four other inputs for the storage, which are to the left of the main table. So this is the main table. If you go to the left over here, these are the durations of the storage. So you can change the minimum duration of the storage of the pumped hydro here. You can change it from 10 hours to 15 hours. This is in hours. And as you change it, that will change its peak power capacity, the maximum amount of power it can output. You can do the same for the battery storage, the fast charging, by changing its duration. So I've got 3 hours as its minimum duration. So if it was working at 100%, it could discharge power for 3 hours. You can change that to whatever you like. And when you change that, you change this value here, which is the peak power output from the battery storage, which here is 60 gigawatts. It's simply, to work out the peak power, it's simply the energy, 300 gigawatt hours divided by the minimum duration, 5 hours. So 300 divided by 5 equals 60 for the pumped hydro. 300 divided by 15 equals 20 gigawatts of maximum power. I'll change this back to 3 hour duration. The other input is the charging efficiency of the pumped hydro. I've set it as 70% charging efficiency. That means it loses 30% of the energy being used to charge it as it's charging. Only 70% of the power that is being used to charge it goes into the battery to help, into the pumped hydro to return water into the upper reservoir. The other 30% is lost as heat. For discharging the pumped hydro, I'm having it discharging at 100% efficiency. So I'm saying it's not losing any power while discharging. For the battery storage, and this goes for the EVs as well because they are also batteries, I have given them a 92% charging and discharging efficiency. It is over here in cell BS22. So I'm saying it has 92% efficiency when charging, so it loses 8% of energy as heat. And it has a 92% discharge efficiency, so it loses 8% of its energy as heat while it's discharging. And that is in the calculations, which I'll discuss in a later video. Okay, so as I pointed out, the point of the model is you change these values up here, the amounts of solar, the amount of PV. Sorry, I didn't discuss nuclear, I forgot about it. For nuclear, if you want to increase the nuclear capacity on the grid, you change this number from 1 up to however much you want to increase it to. So it's a multiplier, it's not a capacity. The current nuclear capacity on the grid is about 95 gigawatts, 96, something like that. So this simply multiplies it by, if you want to increase it by 50%, you would put 1.5 in here. So you'd be multiplying that 96 by 1.5, and you'd have 50% more nuclear power on the grid. If you think nuclear generators will close down over the coming decades, you might have less. You might say 30% of them will close down, so there's only 70% of the current generating capacity. So there you can reduce the amount of nuclear power, or if you think they'll all close down, you can set it to 0. Do not put in negative numbers. If you put in negative inputs, you'll get stupid outcomes. I have not safeguarded it against putting in ridiculous values in the input column. It is up to you to use the spreadsheet responsibly. Okay, so you can change the inputs for wind and solar capacity, for the fast and slow charging storage capacities, for nuclear capacity, and see how the different builds manage to supply power to the electricity grid. You can see the results, the outputs in the graphs, and also in the results table. The idea is to find a build that works for all of the data. So this is just 2021. You'd have to put the same data into 2022 and 2023 to see if supply also met demand in those situations and how it worked. Now this is where I'm going to finish this video. In the second video I'm going to include some variable demand. So what happens if we want to include, turning the electricity grid, the current electricity grid, into 100% renewable supply doesn't get rid of all fossil fuel use. There's still plenty of fossil fuels being used in road transport, as well as rail and planes and shipping. But road transport, which could be easily electrified by turning to electric vehicles, and there's also a lot of natural gas being used in the US and Germany, both in residential and commercial use for cooking and heating, especially space heating, and also there's a lot of natural gas being used for industrial purposes in the US and Germany. So in the next video I'll explain how that type of demand can be included in the model and how you can use the model to completely replace the fossil fuel uses in that type of demand. So you'll be able to find a link to part 2 of this video series where I do this in the description below, and I will talk to you again then.